Hey there, Scholar! Welcome back to another exciting edition of the Daily Scholar. Today, we aren't just memorizing boring facts. We are putting on our detective hats and diving into the ultimate cheat code for understanding how the universe works, the scientific method. Think of the scientific method as your official playbook for solving real life mysteries. Whether you're trying to figure out why your phone battery drains so fast or why your dog barks at the mailman, this is the exact step by step toolkit scientists use to turn wild guesses into hard facts. So today we'll be going over what it means. What does the scientific method mean? The different parts, the step-by-step explanation, the process. And then number 3, we have the sample lab for better understanding. So we'll be going over the definition of the scientific method. So, the scientific method is a logical, systematic process that scientists use to explore observations, test ideas, and answer questions about the natural world. It relies on empirical evidence, repeatable testing, and objective analysis rather than assumption or guesswork. So, the parts or steps of the scientific method. So first we'll be asking a question or observe. So identify a specific problem or phenomenon you want to understand based on an observation. Now let's conduct background research, gather existing information, and learn what is already known about your topic. Next, form an hypothesis. Form a hypothesis. Propose a testable explanation or prediction, often formatted as an if then because statement. Next, you have to perform the experiment. Design and carry out a control test to collect data by changing only one variable at a time. Next, we analyze our data. Examine your measurements, calculations, and observations to identify patterns or trends. And finally, we draw conclusions. Determine whether your data supports or refutes your hypothesis and share your findings. Now, let's go over the Pendulum's Pulse Visual Lab Guide Sample Lab. So, this lab will be broken down into 4 distinct visual panels covering the 6 steps of the scientific method you will use to determine whether mass or length dictates a pendulum speed. All images apply the rigid requirement for safety equipment, goggles, and gloves, and focus on ensuring all parameters are defined only by names and illustrations, not formal definitions. So the pendulum's pulse is a very simple lab, and it is really easy to understand. And yeah, so let's start now. Panel 1. We'll be first starting with observation and question, and the second one, hypothesis. The starting point of any experiment is careful observation. The first image captures a student analyzing a standard symbol pendulum swinging back and forth. Based on this observation, the primary question is formatted. What determines how long it takes for a pendulum to complete this one full cycle or its period? So for this particular lab, your assigned variable to investigate is the length of the string, which is visibly circled in the image. And next, we'll be going over the following this question. We must generate a testable prediction. The second panel transitions into the hypothesis phase. A clear, typed, if then because statement is visible. If the length of the string is increased, then the period of the pendulum will increase because it must travel a longer path at the same force. The underlined text highlights the group's specific variables, directly referencing the assigned question. This hypothesis is now ready to be put to a control test. Next, we do panel 2. Number 3, plan an experiment. This is the control testing. Okay, so the second visual, based on the middle top section of the overview, illustrates the critical planning phase. This is where we ensure the test is fair. A detailed checklist is displayed along an annotated diagram of the lab table. all safety gear is worn. For this group, the independent variable, which is the only thing being changed, is explicitly stated as string length. To isolate its effect, the dependent variable, which is what we are measuring, is defined as the time for 10 swings or the period. Crucially, the non-circle variable or the mass from the first step is now defined as a controlled variable. The illustration must provide this. A detailed checklist specifies A. The mass of Bob, example, set to 100 grams. B. Initial drop angle, for example, set to 20 degrees. And number last but not least, string type and air movement. And for like you can say like use same string, no open windows. This table setup is labeled, showing the 100-gram mass attached to a string and a protractor indicating the 20-degree launch point. The control values 100 grams, 20 degrees are specified as example values, but by defining these fixed parameters, the experiment can commence, focusing purely on changing the string length. Now let's go over panel 3. Number 4, procedure and analyze data. The third visual, focusing on the bottom left section of the diagram, brings the experiment to life. A single clean panel illustrates the actual testing sequence. Students, wearing all required safety goggles and gloves, execute the plan. The image flows through 5 key procedural moments. Number 1, setup. Step A. The student verifies the control values and prepares the first length, for example, 25 centimeter string. Number 2, experiment. Steps B, C, and D. The main action. A primary timer releases the bob at the precise 20-degree angle. The secondary timer starts the double stopwatches. The pendulum completes exactly 10 full swings. Number 3, record. Steps E and G. Check consistent stopwatch readings and record time for 10 swings, 14.2 seconds. Number 4, we repeat. Step H to I. An arrow illustrates the critical loop back to setup, with the independent variable now changed to a longer, example 50 centimeter string. Small inset images show with different string lengths 25 centimeter, 50 centimeter, 75 centimeter being utilized, proving length is the variable in motion. The image visualizes the collection of raw data, time for 10 swings, which is necessary for the next step. Panel 4 will be going over the number 5, data and conclusion, and number 6, draw conclusions and communicate results. The final image, derived from the bottom, middle, and right-hand panels of the overview diagram, synthesizes all findings. The data template from the overview is populated with clean, calculated values and presented with its final conclusion. A clear line graph shows the relationship. String length meters on the x-axis versus average period in seconds on the y-axis. The data points form a precise linear trend, visually demonstrating that a longer length results in a longer period. Based on these averages, the conclusion is drawn and communicated. Conclusion: the data did support our hypothesis. As string length increased, the period of the pendulum significantly increased. Scientific reasoning: Newton's laws and gravity. A longer string forces the bob to travel a greater linear distance in each cycle. Since the gravitational restoring force is identical, it takes longer for the bob to complete the full path. Critical reflection: sources of error, human reaction time, and small angle variations are identified. Synthesis: a comparison graphics, teal versus blue, check versus X, compares the results of the length group to the implied results of the mass group. Mass does not significantly affect the period. The entire sequence, from initial question to final definition-free synthesis, is now visually complete. If you enjoy this video, please like and subscribe. Also, follow me on Twitter by searching up The Daily Scholar. Thank you for watching. See you next time.